Hey guys, what's up? Eddie Aho here with KissAnalog.com. Today we're back here with the Class D Amplifier from Orchard Audio, the Starkrimson Ultra. This is the Ultra module. Got two of them, one on the bench, and I didn't take it up to 100 watts or higher. It's rated for, I believe, 250 watts. It's rated for 250 watts into 8 ohms and 125 into 16 ohms and all the way up to 500 watts into 4 ohms. So I like the way it doubles for each ohmage. It gives a linear power growth, you know, with your voltage. So I like that. It gives a linear power growth with your ohms. So I like that. Shows robustness, I believe, in an amplifier. So this guy, we're going to test this at 100 watts and see how hot it gets. We're going to look at distortion and, you know, spectrum and other things too. Okay, we're gonna look at efficiency, that kind of thing. So yeah, let's come over here and let's do it. Okay guys, just like in the other video, I've got a whole bunch of connections to this. I've got a couple different scopes hooked up to it, but just quickly, the inputs coming in here, it's a bridge configuration. There's two FETs here, two GaNs from GaN Systems, and there's a thermocouple on these two, and here's the part of the LC filter, the big inductor here, and the capacitors on this side. And on the other channel, we've got the control chip, the two GaN FETs, and the other inductor comes to the other side. So one side's driving this terminal, one side's driving this terminal. These two terminals go to my 200 watt 8 ohm load right over here, the silver thing, just off the camera here. Okay, and then here's the signal generator, and we're going to use a Sioki meter too. I'm going to show you that in a moment. And we're putting this input signal here. The voltage for the driver to drive these GaN FETs is coming in here, plus minus 18 volts for the circuitry on the input of the amplifier, and then the 31 plus minus 31 volts for the output section. So I think we're all set up. I've got my picoscope all connected with a bunch of differential probes. Differential probes going to my GW Instech scope. Another set right here. And then more differential probes going to the Pico. But I'm going to show you the GW Instech. We're going to just do this quick, kind of like the last video, but we're going to just take it up a little higher power. And then I'll take a thermal picture of this as it heats up. Okay? And just in case you forgot, those are the only two heat sinks on this, just on the opposite side of the GaN FETs. Okay, not requiring a lot of heat sinking at all. Now this guy's capable of 500 watts. Now in 8 ohms, it's 250 watts, I believe. We're going to put 100 watts in 8 ohms. Okay. All right. In this view, you can see the Sioki. I love these meters. We're going to look at the true RMS voltage here at the 200 watt 8 ohm load, and we're going to look for just over 20 volts, because 20 volts will give us 100 watts RMS. And then you'll be able to see the generator here as I turn up the input voltage. Right now it's 2 millivolts. We'll crank that up to get 20 volts here. Okay, now in a moment you're going to hear the power supplies turn on, and you'll be able to watch me crank this and see the voltage come up, and then I'll show you the scope after that. Alright, I'm going to crank up the voltages right up here, my power supplies. Okay, so what I'm going to do is first turn on this one. Well, actually I'm going to turn on this. This is plus minus 18. And there's no voltage going to the board until I hit this output button. Now when I turn this on, I'll make sure the voltage is down. That's my plus minus 31 volts for my main output. So, and then over here I've got this on, and then I'll turn this on. This is my driver voltage for the negative side voltage rail. Okay, let's go ahead and do it. I'll turn this on. Okay, output's on. It's got about 7 milliamps per side. And then we'll bring this up, and both sides will have this voltage, and we'll see the current here on each side. Okay, 31.6, there's really no current yet. See, no current. Both sides have 31, plus minus 31.6. So I'll leave one on current and one on volts. Okay, then I'll bring up the driver voltage to 15 volts. Alright, we're all set. Now let's look at the output voltage come up. And with 2 millivolts, we got 31 millivolts on the output. Okay, now we're 100 millivolts, 200, 3, 4, 5. Okay, 700 millivolts, 900 and 1.1, and we got, well, we're just over 100 watts. Okay, no problem. And I don't know if you can see the red LED here. There's a couple other LEDs for over voltage, over current if we had a problem, but we don't, so everything's good. And then going up to the scope. Okay, I'll just zoom in on the scope here so you can see that. And there's waveforms. Okay, green one is 20.6 volts, and input is 1.13 volts. And they're in phase, you can tell. Signals are looking good. And let's go look at the spectrum. We're looking at the spectrum on channel 4, which is correct. We're not using channel 1. I'll zoom out. We're not using channel 1. Channel 2 is the input, channel 4 is the output. Now, I'm kind of zoomed in, and what I'm actually looking at is, here, let me show you the frequency and span. This is, start frequency is 1 hertz, stop is 3 megahertz. Okay, so where my cursors are right now, I just want to show you the switching frequency. Broad spectrum, that's called broad spectrum, it's pretty wide. I'm thinking the switching frequency might be dithering a little bit, I'm not sure, but it's 735K, and then this is a fundamental, okay? So now let's go back and change the stop frequency to, say, 100K. Okay, it looks like 100K we're good for, start. It kind of changes it when I change these. Okay, 1 hertz, 100K. Alright, so now we're looking good. And you can see it's all the way over here, our 1 kilohertz signal. There's a marker, see the little green thing here? There's a green marker up here. And this little window right here tells you what that marker's reading. It's 1 kilohertz and 25.6 dBs. I'm getting a reflection on that screen, sorry about that. Alright, so that's looking pretty good, right? I'm going to change the frequency to 10 kilohertz, kind of put it in the middle of the screen somewhere. Light too, and 10K is right here. Each grid's 10K, so we got 10K here. A second, the harmonic here is really low, and then this harmonic looks like there's a little spot up here. Here, let me get rid of the cursor window. Okay, there's what we're looking at. My THD meter, the Keithley. Alright, so the Keithley THD meter is reading 0.014. Now, one thing I want to mention is my Unity generator is a nice generator. It's inexpensive, small, nice, easy to work, but it doesn't have the lowest distortion. Doesn't have the highest either, but what we're mainly seeing there is the distortion amplified through the amplifier. So the amplifier is actually a lot lower than that, probably. So, alright, so we can see the spectrum here, right? Now, here, what I'll show you, something kind of cool on this scope. Here, I'll zoom out so you can watch what I'm doing here. Okay, what you do is you come up here to this little search tool, and we can come up here and we can get a table. And we can turn on the table, but before we do that, what we can do is say the method, what we want to do is through a threshold, and then we can bring this threshold up here somewhere, let's say right above minus 40 dB there. I'm at 36.8 dB, and I only got one, well, hold on a sec. I've got to include more peaks, so I'm going to say I want to, I can only go to 10. I just rotated it, only found 10 there. So let's come down here, see if I can get more. Nope, I only get 10. So I can max out at 10. I didn't know that. Alright, so I'm just going to bring it right here, say right above 40 dB. Okay? Now let's go to that table, and I'll just show you the table. Now let me zoom in so you can read it. Alright guys, so let me just show you this. Now 10K is our signal, 25.6 dB. The next closest one is probably at 30K minus 11. So that's still 36 dB signal to noise ratio. Now up here, 1K, there's actually a signal. That's what we call a subharmonic. And that's a minus 24. So there's over 40, 50, there's about 50 dB of headroom. So you can see the table and just take that 25.6 and subtract whatever you see. And you can see that most of them, the closest one, like I said, is minus 11. Everything else is 20 or 30 dBs down. And so we've, and every 20 dB is a 10x factor. So it's looking pretty good. I think that's why your distortion's reading so low. Alright, let's go down here and look at the board. And I got to get my thermal camera, and I left it, it's in my bag, so I got to go grab it. Meanwhile, this board's going to heat up. But that's okay, because you know what? I don't feel any heat at all coming up. As a matter of fact, they're almost cold to the touch. They're barely above room temperature, and touching the board, I don't feel any heat. Here's the drive control chips. I don't feel any heat off them. I like to feel the top of the cap sometimes, and they're cool. If you ever feel an aluminum electrolyte getting warm or hot, that cap is underrated. Okay, I'm feeling the thermocouple. I barely feel any heat, guys. I'm going to get my thermal camera, but I'll bet you that's not more than 5-degree rise. And we've been running here for a few minutes. Long enough for my Hioki to want to time out. So I'm not sure how long that is. I think it's 5 minutes, but might be 3. But anyway, I don't know how long it's been sitting there. Now my power supplies, let's go look at my power supplies. Alright guys, so here's the power coming out of the main 31.6 volt rail, almost 0.9. So actually, and remember we've got to double this, so it's like 62, 63 volts times that, so roughly 60 watts. And you know what? We have 20 volts. We're at 20.4. That's actually 50 watts. I think I said that was what we need for 100 watts. That was a mistake. We actually need 28.28 volts. Okay? So I'm going to go ahead and crank up the input, and then I'll come back down and show you. Well, here, let's just do it. Alright, back down here. So we're going to come down here to amplitude, and let's bring that up until we get 28.28 volts. Okay, that's a little bit high, so we are going to be right on the number here. Okay, that's barely over 100 watts. Okay, everything's looking good there. Nothing's really getting hot yet. Now that resistor might get hot because it's rated at 200 watts, so that's going to get pretty hot. So let's come up here and look at our voltage. Okay, now down here, 18 volts, it's still not even 8 milliamps. And up here, we're at 1.7 amps, basically at 31.6, so double that, and that's our input power. I got 52.45 watts, so double that. 105 watts basically. So yeah, pretty darn efficient. We're only losing 5 watts. And this guy over here is drawing no current at all, that driver. Very little. Okay, now let's go look at our signal. And that's not looking too good, but my distortion meter is still saying, that's still saying 0.011, which is mostly the generator. So I think this is because our signal's off the screen. And so we're chopping it. Okay, now let's go back to the spectrum. It should look better. Well, not too much better. Alright guys, so there's the spectrum right there. And get rid of the window there. So yeah, we're seeing a whole bunch of peaks, but they're down here at minus 20 dB. So our input signal is about 30 dB almost, and then down here is minus 20. Alright, so yeah, it's a lot, you know, a bunch of little stuff down here, but you know, the signal noise looks good, the distortion looks good on the Keithley. So let me go to my search tool and let's do the threshold and bring that to right about there, just see if anything's above, say, -20. That's -20. So let's go to the table, and there's a few of them right hovering around 2017, and our signal's 28.8. So that's the signal noise ratio, 28.8 -1 of those. So it's about, you know, 40, almost 50 dBs, and every 20 is a 10x factor. So it's over 100x below the signal for signal noise. Okay, let's go back down to the board. Now, as I'm kind of filling the inductors, they feel very cool still. The control chips feel cool. I don't really feel any heat coming off the board, so I'm going to touch the FETs, and they feel cool too. Maybe 10 or 15 degree rise, maybe. I'll go get my thermal camera and let this bake a little bit. Alright guys, I do smell some heat, but it's mostly my load resistor. And the temperatures on these things look like they're kind of getting stabilized. I see I see 64.3 degrees on the GaN FETs there. There's a close-up of it. You can see the 64 degrees, and there's a chart there, white, red, yellow, green, blue. So there is another regulator. There is another regulator up here that's kind of getting warm. But look how cool the inductors are. Yeah, the FETs, you know, not bad. Alright guys, so yeah, I mean, it's sat here for a little while longer, and they have stabilized in temperature. Maybe I'll take one more picture of this, and there I am. Alright guys, so what do you think? Now I did see the distortion, you know, even though it's still low, I saw a spike starting to pop up when I went over 50 to 60 watts. It could be that I don't have the full voltage on the power rails. It's rated for, I'm at the low end, I'm at 30, 31 volts, and they want 30 to, I think it is 41 volts or something like that. So I'm at the low end. It could be due to that, but it looked super clean up to 50 or 60. THD is basically just reading what my generator is putting out, so it's putting out a real clean signal. But then at some of these higher frequencies, especially now, I went all the way out to 100K, and so I could start seeing them creep in as I took it up over 60 watts. And as I got to somewhere, I don't know, 70 watts or something, it kind of creeped in a little closer. I should have showed you that too. Sorry about that, but maybe I'll be able to keep this and do a little more testing. I don't know. What do you guys think? I have to ask, because this is a loaner. I have to return these two boards, and it was really nice that he sent them out to me and let me play with them. Okay, they do have the GaN FETs from GaN Systems. Let's take a look at their data sheet real quick.
All right, so here we are at GaN Systems. Look at this FET. I mean, this thing is teeny, but look how thin it is. So it gets rid of temperature really well. Now here's the symbol for the GaN FET. This is their symbol. You notice they're not showing the body diode. There is kind of a body diode, kind of, sort of. We'll cover that in another video. But because there's not a typical body diode like a MOSFET, there's zero reverse recovery loss. See this right here? And also notice this fast and controllable fall and rise times. That's the beauty of GaN. That's one of the beauties. Okay, so let's look at this. RDS is 7 milliohms. IDS 90 amps. Now these two are the things you a lot of people compare on FETs, but they are important, but that's only part of the story. Look at this. 90 amps at 25C. Once you warm up, but you'll never see 100C, come on. But anyway, 65 amps. And pulse current, 140 amps. Here's a beautiful characteristic of a GaN FET. Junction to case, that's the resistance, thermal resistance, junction to case, 0.55 degrees C per watt. That's really low. That's awesome. Even this, junction to ambient, is 20 degrees C. You know, a lot of times these small kind of devices, you'd be used to seeing 40 or 50, so it's really low. Okay, so now here's some of the other specs you kind of want to see. The threshold voltage is very low. It starts to turn on at 1.1, typically 1.7 or max 2.6. So it's very low voltage. Doesn't need a lot of voltage, so you're not charging capacitors at the gate at a very high voltage. So besides the capacitors being very small, see these numbers down here? Besides them being very small, you're not charging them very high. You don't need to charge them very high. 5-6 volts max. And voltage is a squared function. So if you have the voltage, it's like 4 times less energy, essentially. But anyway, I mean, that's just a quick look at it. But so here's all your capacitances. See how small those numbers are? Now, here's a number they come up with. Total gate charge, 8 nanocoulombs. Very low. Here's another graph I want to show you. See figure 6? It looks like a MOSFET, you might think, just looking at it quick. And hey, it's about 3.5 volts, this little shelf thing. So it charges up, and then it has this dead time where you have to really push some energy into it to get to the next threshold. Well, you see that in FETs. But if you look closely at this, one thing is these numbers down here are very small. And the number between here and here is very small. So we're essentially looking into a zoomed in version of what a MOSFET would look like. A MOSFET would look horrendous zoomed in like this. It would be a lot bigger numbers. This plateau would be wider and so on. So that's another great advantage of the GaN FET is just the gate charge and this like this little plateau that you hit when you're driving the gate. You want to drive it through that. So that means right around here, you're going to take the step where you have to, it looks like charging a big inrush current to a capacitor, and then you go up. So anyway, I just wanted to point that out too.
Yeah, so the thing about GaN FETs, what makes them, you know, it's not just a marketing gimmick. They're more ideal switch. A MOSFET is more ideal than a BJT transistor. But, you know, the idea is that when you say turn on, you don't want a delay. And then once it starts to turn on, you want that ramp to be real fast. And, you know, ideally, you'd want no ramp. And you want no delay from the time you say turn on. So GaN FETs are getting closer to that. When you tell them to turn on, there's a lot less delay. They turn on a lot quicker. So, you know, with Class D amplifiers, technically, you know, you would think that they would have a better sound because you would need less filtering, even though this board has really big LC filters, which is nice because they're most Class D amps, the L's are a little bit small and they get kind of warm, but these were cold. So, but you know, 100 watts, so, but still, you know, even if they got twice or 3 times as hot, I mean, maybe they'd get warm. So they're huge. So the LC filters are really nice. All right. So the thing with GaNs is that when the transistors are switching on and off, it's an H bridge. So you have the load tied between 2 transistors on this side and 2 transistors on this side. And the 2 corners turn on, pulling the signal this way, and then they turn off, and then these turn on. Well, you can't have all 4 be on at the same time, so you want to set some dead time. But plus, like I said, they're not perfect. There's some ramp time, delay time, and there's also the tolerance in that, you know, like how much, you know, the delay's not a real fixed amount. So you have to have some dead time to make sure that one set of FETs is off before the other ones get turned on. Otherwise, you get what they call a shoot through, you know, and that kills FETs. So you want the current to go through the speaker from one corner to the other corner, and if all 4 FETs are on for a moment, then this FET would be shorted to this one below, and same thing on this side, you know, or even if just two of them happen to be on, because maybe the tolerance between parts, you get two parts so they have to set the dead time is the whole point. And with GaN FETs, because those times are so much tighter, you can have a lot less dead time. And so that dead time in between is a blank spot. And so when you look at your pulses, you want your pulses like small, you know, you want them to get narrow and big as the voltage changes, and the dead time between is not good. You have to use the LC filter to smooth those off to keep it continuous, the signal, so it looks like a sine wave instead of, you know, a bunch of square waves put together. So anyway, if you I think you probably get what I'm saying, right? So that's why GaN FETs are more ideal for Class D amplifiers. Technically they should be, and efficiency should be better too. And the reason why efficiency should even be better with the GaN FET is because since there's not that slow ramp on, like in a MOSFET, I'm saying relatively slow. MOSFETs are still fast, but as the thing's turning on, it's ramping up. You imagine a triangle shape there from the time it goes up. Well, that time that it took to ramp up, the current is ramping. At the same time the voltage is ramping. Current times voltage is watts, right? So you want that to be near zero. You want that ramp time to just go from, you know, when the current's not flowing, from the current's flowing, you want it to just flip up, like real fast. So you don't have that overlap and that power loss, and that's, they call it switching losses. You don't want that. That's one of the switching losses. The other thing is just turning the darn thing on, turning it off. You know, GaN is, GaNs and FETs, MOSFETs are all voltage driven. You put a voltage at the gate, turn them on, right? But you also need current. They're not like a BJT that needs a lot of current, and then they amplify the current through the collector. You put voltage at the gate, turns them on. But there's a couple things going on there. There's like a capacitor from gate to source. There's also a capacitor from gate to drain. And the voltage from the drain is dropping, right? So that means that capacitor is changing, and it's dropping a lot. So that capacitor has a large charge cycle change. And so it's part of your gate charge, charging those two capacitors on and off. And with GaNs, they're just a lot smaller, so you're not charging so much energy in them, so that switching loss is gone as well. So anyway, that's why GaN FETs and Class D amps should be better than a FET. I say should be because the designer has to take all that into account, get rid of the dead time he doesn't need, and those kind of things, and design the LC filter appropriately. In this case, it looks like a good design as far as I can tell. I haven't done any math, I haven't done any analysis, but just the selection of components, the quality of the capacitors and so on, it just looks good. Looks like a good design. They are expensive. Yeah, there's no doubt about that. $1,000 for the two boards. Well, a little bit more than 1,000, right? So they are spendy, but that's because they're new and not a lot of competition right now. So anyway, there you go. Let me know what you guys want to see. If you want to see something else, I can reach out to see if we're allowed to keep them a little longer to do any more tests. But he probably wants to get these boards back, and I've been super careful with them. As a matter of fact, I've only tested the one. Yeah, I just don't want to pay for these things. So yeah, sorry about that if I've been a little ultra careful. It'd be great to actually power them both up, and you know, I've got a box down here. It'd be nice to put them in the box with some power. And I have an audio friend that loves sound, loves music, and listens to music all the time. He loves the Class A amplifier built. It'd be cool to have him compare the Class A with this to see if because he has no stake in the ground. He doesn't care one way or the other. He just wants sound, and he really digs the Class A. He really loves it. And I mean, he's head over heels on that thing, man. That's just an awesome amp. So it'd be cool to see if he was as excited with the Class D. But yeah, maybe I'll have to find one I can afford so we can build one up and put it in a box, right? All right, hey, thanks guys for watching. I appreciate it. Thumbs up to the video if you liked it. That really does help YouTube analytics. And thumbs up to Orchard Audio for letting me, borrow these things. Leo is the guy over there that you can contact. He's great. He's been super responsive when I've had questions. And thumbs up to Orchard Audio and to all you guys for watching the videos. Thank you. And we'll see you next time.